Okay, so this is what we have learned in terms of the concepts in work energy so far. So let's start with another application example today. So for example, we have a smooth surface like this. Okay, and now a particle is moving here with a speed of v naught. So it comes sliding down like this, reaches this point here at some point of time with a speed v1, and then from here it goes into projectile motion and hits this point with a speed of v2. Okay, so a particle has v naught equal to, let's say, 4 meters per second at the point A as shown. Okay, and all this is smooth, so this is a smooth surface. There's no friction anywhere. Oh, we've already written that smooth. So there's no friction anywhere. So given that h1 is equal to 20 meters and h2 is equal to 25 meters, take g as 10 meters per second square. Okay, so we have to apply the concept of work energy, apply the work energy or the work kinetic energy relation to find the speed v1 at the point B, and then to find the speed v2 at the point C. Use the work kinetic energy relation Okay, so just try this out. Okay, yeah, Tantresh, let's work out the question. So what we can see here na, is that as the particle is going from A to B, the work done by normal reaction will always be zero. Because while the particle is at a position like this, normal reaction and mg, it's such that for a small displacement, you can see normal reaction is perpendicular to the displacement. When the particle is at a point like this over here, again what is happening? Normal reaction will be acting in the direction which is perpendicular to the tangent. Okay, if this is the tangent to the curve at that point, normal reaction will be acting like this, whereas the small displacement ds, so that will be like that. Okay, so work done by normal reaction will be zero. So in all there are two forces acting on it. Okay, so work done by net work done is change in kinetic energy. We are using that relation. So the net work done should be the work done by mg plus work done by normal reaction, because at any point of time these two forces are acting. Now for work done by mg, we just have to use this, because mg is a constant force. So you can see that if we take our xy system like this, then we can write mg as minus mg j cap. Okay, and if the displacement is some x I cap plus y j cap, we can see that this dot product will just become minus mg into y, where y is the y component of displacement. So we'll come to application of this. Okay, so we get this kind of formula. But when it comes to work done by normal reaction, it should be integration n dot ds, because in general normal reaction is variable, but that will become zero, because what is happening is, as I told you, at any point of time, whether we are here or here, the normal reaction is always acting in the direction which will be perpendicular to the instantaneous differential displacement. यहाँ पे displacement ऐसा होगा at 90 degrees, यहाँ पे displacement ऐसा होगा along the tangent, so at 90 degrees to the normal reaction, because normal reaction always acts perpendicular to the tangent at the point of contact. So this will be zero, because n is perpendicular to ds everywhere at all points. Okay, so this becomes okay. So putting these two things back in the work energy theorem, we get that minus mg into y, where y is the y component of displacement. This quantity is our change in kinetic energy. Y is nothing but the y component of the displacement. So now we have to just specifically apply this to the different points. Okay. So for example, the first part, going from this point A to this point B over here. Okay. Or this point whatever. Okay. So here the speed was V0. Here the speed is V1. So we can see that the displacement will have some kind of X component, which doesn't really matter. But it will have a Y component. Okay. So this, for this from A to B, okay, the y component of displacement will be minus h1. Okay, because we have taken y-axis upwards. Remember. Okay, so the y component of displacement from A to B is minus of this height. Okay, so this will become mg h1 is equal to half m v1 square minus v0 square. So v1 will become square root of v0 square plus 2g h1. and now you can substitute the values. Okay. Now similarly, once you got V1, after that B2C is even simpler, because what's happening is there is no other force acting. B2C, there's only gravity acting everywhere. There's no other force only acting. So for B2C, we can see that just it is work done by mg is change in kinetic energy. Okay. So again, if this height is h2, the work done by mg will become mgh2 is equal to half m b2 square minus b1 square. So now you will get b2 as square root of b1 square plus 2gh2. Okay, and you can use this relation, this first one over here. So you will also get that v2 is square root of v0 square plus 2gh1 plus h2. Okay, so you can use this also. So after doing all that, you will get v1 as square root of, so v0 was 4 meters per second and h1 was 20. So square root of 16 plus 400, square root of 416 meters per second, and v2 will become 16 plus 20 into 20 plus 25. Okay, so square root of 45 into 20, that is 900. So 916 meters per second. So that will become our v2. So finally, these are our answers. These values, right? So I'm just minimizing this a little. Go through it once if you need to. Okay. So the important thing is how we have found out that the work done by normal reaction is going to be zero because of this and this part here. How we are getting that the normal reaction is always going to do zero work. Okay, just make a note of this. We will discuss more next. If there's any doubt in this, please let me know. Yeah, you can do that also, but we have to understand that theorem first. Okay. Yeah, Prince, I'll explain again. Okay, so see, we are having a general theorem that net work done is equal to change in kinetic energy. Okay. So when the body is going from this point A over here to this point B over here, okay, it's following this kind of a path. So at any point on the path, you can see na, ki the normal reaction acting on it will act such that the direction of normal reaction is perpendicular to the direction of the instantaneous displacement. Okay. Whereas mg will act on it in such a way that the direction is vertically downwards. कहीं पर भी हो, whether it is here or initially also at this point, you can see that normal reaction is always acting at 90 degrees to the differential displacement. Okay, so this net work done, it is work done by normal reaction plus work done by mg. So this term will be 0, whereas this term will be minus mgy, where y is the y component of displacement. Okay, yeah, so I'm explaining. Okay, so this should be equal to the change in kinetic energy. So as you're going from the point A to B, बता रहा हूँ ना, I'm telling that only. So as you're going from A to B, okay, what is your y? The y component of displacement is minus h1 na beta, because this height difference. So see, A is a point over here and B is this point over here. So from here to here, the displacement vector is this now. This is the displacement vector. So इसका vertical component और horizontal component कितने हैं? This is h1 and this is some x1, let's say, from here to here. So this displacement vector is what? It is x1 I cap minus h1 j cap. No? So the displacement from A to B, what is the y component of displacement? It is minus h1. Is it clear now? So from A to B, the work done by mg, which is mg dot s, which becomes minus mgy ना, वो कितना हो जाएगा? Minus mg into minus h1 ना. So it will be mg h1. Is it clear, Prince, this equation? Okay. So that only is the work done, na? So that is equal to the change in kinetic energy. Now at A, the speed is v naught. At B, the speed is this. So change in kinetic energy from A to B, that is how much? Half m v1 square minus half m v naught square. Got it? No. So equate these two things. The work done, net work done by with the change in kinetic energy. So this equation next, na, this equation only for A to B, it becomes how much? Mg h1 is equal to half m v1 square minus half m v0 square. So from this we get the relation that v1 is square root of v0 square plus 2g h1. And then same thing you apply from B to C. Okay. So this, when you substitute, it came out to be square root of 416 meters per second. Okay. And then same thing B to C, when we saw, it became v2 is square root of v1 square plus 2g h2. Okay. And on substituting, that became square root of 916. Okay, so hope this is clear. Okay, next up we will look at some more examples of work done by variable force. Okay. So on the first day of work energy, we discussed about, yeah, sir, I'll scroll up. Okay. Understood now after equation 2 what we've done, sir? Okay. V1 का वैल्यू को सब्स्टिट्यूट कर दिया ना यहाँ पे. From this we have substituted V1. So we got, okay. All right. So let's go back to some more examples of calculation of work done by integration. In this case, we didn't have to do any integration because we saw normal reaction is doing zero work. Na? So an mg is a constant force. Let's look at examples of work done. Okay. So application of integration. Okay. So that day we had seen one-dimensional examples, work done by spring force and work done by another one-dimensional example. Now today, let's look at this kind of situation. A particle is moving in a two-dimensional plane. Under the action of a two-dimensional force which is variable. Okay. So let's say at any arbitrary point x comma y, when the particle is located, there is a force acting on it which has both components x and y, and it's a variable force. So a variable force F given by the relation, it is alpha x square I cap plus beta j cap acts on a particle P of mass m at position when the particle's position is x comma y. Okay, so here alpha and beta are constants such that X, Y are in meters. So the force is in newtons. Okay. Now this particle makes a displacement from the origin to this point over here, let's say. Which has coordinates 2a comma 3a. Okay. Now the particle can make the displacement either by a specific path like this. Okay, so this is the first path. Or it can alternately also make the displacement by a second path which is like this. So we have to calculate the work done by this force for the displacement of the particle P from the origin to the point A, which has coordinates 2a comma 3a, by path 1. Okay. Then again from the origin to the point A, but by path 2. And we will come to a C part after this also. Okay, just you have to first work this out. So take down the question. I will explain step by step how to work this out. Yeah, okay, so let's understand how to do the first part. So what is happening here is initially I'm going along the x-axis from the origin to a point like this one whose coordinates will be. So my destination is this point here, which is 2a comma 3a. But my path taken to reach this point is this path over here. First, I'm moving along the x-axis to this point, which would be having coordinate x coordinate 2a, y coordinate 0. Then I'm moving vertically along the line x equal to 2a from the y coordinate 0 to the y coordinate of 3a. Okay, so let me introduce an intermediate point over here b, which has the coordinates 2a comma 0. Okay, so if this is path 1, okay, so the work done by that force F, which was given by alpha x square I cap plus beta j cap in path 1, that work done by F for path 1 will be equal to work done by F from O to B plus work done by F from B to A. Okay. So we'll calculate these things individually. Okay. Now O to B, when the body is moving or when the particle is moving, at any point like this, it has this kind of coordinate, na? Some x coordinate. Okay. So the force which is acting on it at this point of time will be given by this expression. So at any arbitrary point x comma 0, the force acting on it is given by the relation alpha x square I cap plus beta j cap. Okay. Now during that time, that small displacement will be along this direction. Okay. So its displacement will only have an x component for this part from O to B. So the differential displacement will become how much? Dx I cap. So the f dot ds term is becoming alpha x square dx. Okay. So the work done from O to B is becoming integration of f dot ds from the origin to the point B. So this integration will reduce to alpha x square dx from the origin where x was 0 to that point where x is equal to 2a. Okay. So you can see that this work done will be given by this formula. So it will become 8 by 3 alpha EQ. This is the work done from O to B. Okay. That's one part. Okay. Now next, how to calculate the work done from B to A. So when the particle is going from B to A at some in-between point, it will have an x coordinate of 2a, but a y coordinate which is variable. Okay. And once again, the force acting on it will have some general value like this. So at any point 2a comma y, the force acting on it will become how much? It will become alpha into 2a whole square I cap plus beta j cap. This is what the force will become. Okay. But now the differential displacement is along which axis? It's along the y-axis. So this is dy j cap. So now you can see the dot product of these two is becoming just beta dy. Yeah, Prince, I'll do a run through of the whole thing once again. Just let me complete this first. Okay. So the work done from B to A will be the integration of this f dot ds from the point B to the point A. So this is becoming nothing but integration of beta dy from y equal to 0 at the point B to y equal to 3a at this point. So this will become beta y. So you can see that it will become 3a beta. So this is the work done from B to A. This was the work done from O to B. So now the net work done in path 1 is the sum of these two. That's 8 by 3 a cube alpha plus 3a into beta. This quantity is the net work done. Okay. So I'm just minimizing this, go through this once. So see, step by step, everything is explained here. Just go through it, you'll understand. So at any general point, the force is given by this. So when I'm going from, so the path 1, I'm dividing into two subsections. First, the horizontal displacement from O to B, then the vertical displacement from B to A. Now, while going from O to B at any general point on the x-axis, so at any general point like this, substitute the values of the coordinates in the formula of the function, in the formula of the force. This is the value of the force, this over here. And the displacement is along the x-axis, so it is just dx I cap. So f dot ds becomes the dot product of these two things. So that's how we get this. And now that f dot ds has to be integrated from initial to final point. So just substitute f dot ds as this dot product, which is alpha x square, and put the proper limits. At the point O, the x coordinate is 0. At the point B, the x coordinate is 2a. The variable of integration is x over here, and carry out the integration. Now repeat that same process from B to A, where it's going along the vertical line. So the x coordinate is fixed at every point. Okay. But the y coordinate is varying between 0 and 3a. So substitute these coordinates in the formula of the force. Okay. So this is the value of the force, and substitute the displacement as along the y-axis. So it is dy j cap. So f dot ds now becomes this quantity here. So again, f dot ds has to be integrated from B to A. Is it clear now, Prince? So hope this is clear. Make a note of this, please. Now, after you noted this down, apply the same method for the second path, which I had shown. That is the path 2, where you were first going vertically and then horizontally. Between those two same points, you were first going vertically along the y-axis and then horizontally parallel to the x-axis. So how we can calculate the work done in that case? Okay, so is this clear, Prince? The whole first part is clear for path 1. Okay, now we have to repeat that same thing for the second path. Okay, so second time we just repeated for the other path. So that's your second path. Where again the general equation for the force is alpha x square I cap plus beta j cap. So you want to calculate this. Okay, just try this out now. Yeah, so same value is coming na Kanishk. Yes, exactly. The work done would be the same, Tantresh. So you should be getting the same value of work done. Okay, so anyway, let's see one way of doing it. So if this is the point C, we can divide the work done in path 2 into 2 bits, work done from O to C and then work done from C to A. Now going from O to C, we can see that when you're doing this, at a general point like this, your x coordinate is 0 and your y coordinate is varying. Okay, so at this point of time now, your force will become like this and your displacement will also become like this. Okay, so this part, at a general point 0 comma y, your force is actually very simple. It is just beta j cap, because your x coordinate is 0 and your displacement is dy j cap. So the work done becomes very simple to calculate. So just this becomes beta dy from y equal to 0 to y equal to 3a. Okay. So this is 3a beta. So get this value. Whereas from C to A, the work done okay. So now you are at a general point like this, whose coordinates are, the y coordinate is fixed and the x coordinate is varying like this. Okay, so the force has a general value. Like this, and the displacement has an x component only. So at any point x comma 3a, f is that same value. Okay, and the displacement is dxi cap. So work done from C to A will just become alpha x square dx from x equal to 0 to x equal to 2a. So that will give us our 8 by 3a cube alpha. Okay, so the individual parts are different, but the net work done by path 2, which is work done from O to C plus work done from C to B, sorry, C to A. This is becoming the same. So notice that it is same as the work done in the second path. So the work done in each of the paths is the same. So hope all of you understood this properly. So make a note of this, and now next what we will do is we will do a proof that work done for any general path. Which one? Oh, sorry. नहीं वो बेटा उसका x coordinate है ना, that's why in the integration it's 2a. See, this is the limits na beta. So the x coordinates limit is going from where to where. Here you see na, this x coordinate, it is ranging from 0 to 2a. 3 is the y coordinate. Okay. Okay, so this was the second part. Now note this down. Okay. Now we will do a third part for the same question. In that we'll see that for any general path from the origin to the point A, the work done by the force is identical. Okay. So you take any general path, need not be a straight line at all. Okay. Between these two points, we can take any path like this. The work done should be the same. Yeah, that's okay, Prince. Okay. So this is the third part of the question. So if you finish writing down the second part, start working on this. We will discuss. Exactly. That is what we're going to show on mole. In this case, for this particular force, we will be able to say that that particular statement can be made about this type of force. Okay. And through that only we will understand an important definition next. Okay. But first, just show it. Like mathematically, we have to prove this thing. No, see Tantresh, the thing is, it's not always the case. Okay, because see, work need not depend on displacement. Now, work is path integration. If the force is constant, then yes, you can say it will always be the same for sure. But here we can't say for sure. We have to actually prove it. Okay, so just getting to that point only. So let's see. So if we not now talk about any general path from the origin to that point A, how can we calculate first of all the work done for any arbitrary general path? This is our point A, is having coordinates 2a comma 3a. But instead of taking that specific path, which is the combination of two straight lines, okay, if we take any arbitrary path of choice, like this kind of path, let's say, okay, how can we prove this? So let's say we are at some general point like this, x comma y. So from this point, our displacement is along this path, and our force need not be along the displacement, and the force can be at any angle. So at any general point x comma y, the force is given by the equation alpha x square I cap plus beta j cap. Okay, and the displacement now has both components, is dx I cap plus dy j cap. Therefore, work done, which is integration of f dot ds, okay, that becomes integration of alpha x squared dx plus beta dy from the origin, which is having coordinates 0 comma 0, to the point E, which is having coordinates 2a comma 3a. So because the expression is like this, now I can easily separate it into two integrals, okay, like this. And here the x coordinate is changing from 0 to 2a, and here the y coordinate is changing from 0 to 3a. So I can show that no matter what path I take, it will be the same as the value we had got for this two specific paths earlier, and that will be 8 by 3 e cube alpha plus 3a beta for any general path. So this is how we prove this. Okay. Now the reason why I'm doing this question is that we will next at some point of time today we'll see that there are two types of forces: conservative force and non-conservative force. So for conservative forces, the work done is independent of path and it is a state function. Okay. It only depends on the initial state and the final state. Whereas there is another category of force called non-conservative force, where the work done will be different for different paths. So there we say that the work done is path dependent. Okay. So here we can say that this is a force such that for this particular force given by that relation, okay, the work done is path independent. It depends only on state. That is from what position is going to which other position. So make a note of this. This is an important concept here. Okay, so hope this example is clear to all of you. Now, the point I was making earlier, that it will not always be the case that the work done is path independent. Okay, it depends on the type of force we are dealing with. So let's see another example of a force in a two-dimensional situation only. So for example, now we have a situation that the force acting on a particle moving in the two-dimensional plane is given by this. It is alpha x square I cap plus beta xy j cap. This is the force acting on a particle at the position xy. Okay, moving in the xy plane. Okay. So find the work done from O to, let's say, some general point P, which is having coordinates A comma B. Okay, so we will see two different paths again. Okay. This is our first path. And likewise, this is our second path. Now try to work this out yourself. What is the work done in each of these paths? Use the same kind of method like we did earlier. I'll explain to you in a moment, but try this out yourself. Yeah, you can see the work done is going to be different. So for path 1, let's name this point A. So the first one, work done by path 1 is work done from O to A plus work done from A to P. Okay, so when you are at this position, okay, the force is to be like this, because the y coordinate has become 0. Then when you are at this kind of position, the force will have this kind of value. Your displacement is like that. Like this. Okay. So the work done in path 1 will become this plus this. Okay. Now similarly, let's calculate what's happening for path 2. Let's take this point as B, which is having this sort of coordinates. So while going from O to B, you can see that the force will be 0 because the x coordinate is 0. So at any point 0 comma y, the force is a null vector because the x coordinate is 0. So work done from O to B is 0. Okay. And then at any point like this, where your x coordinate is varying but your y coordinate is fixed, there will be some amount of force. Like this. Okay. And your differential displacement will be along the x-axis. This. Okay. So work done from B to P will become this dot product, which is this going from x equal to 0, x equal to a. So this will come out to be alpha by 3 a cube. But this one is 0. So now you can see that the work done in path 2 is 0 plus alpha by 3 AQ. So you can see that they are not the same. See that work done in path 1 is not equal to the work done in path 2. Therefore, in this case, the work done by F is path dependent. Okay, so both types of forces are possible. It need not always be path independent. Okay, so just make a note of this example properly. Okay, so hope this concept is clear, that here the work is becoming a path dependent quantity, so it's not a state function anymore. Okay, so now based on these examples that we've seen, there is two important definitions over here, two types of forces. We'll see that forces can be divided into two categories: conservative forces and non-conservative forces. So if the work done by a force is path independent, then we call it conservative. Then it is defined to be a conservative force. So for conservative force, the work done depends only on the final and initial positions or state. It is independent of the path. Whereas non-conservative force, the work done is path dependent. Okay. So this is the general definition. Now there is one more important property of conservative or non-conservative forces. We'll discuss about that next. Just make a note of this first. Okay, now one more condition we'll see here, that in a closed loop path, okay, or what we also call a round trip, that means a path such that the particle or body returns to the initial position. So in a round trip or closed loop path, the work done must be zero for a conservative force. Whereas in the case of non-conservative force, in a closed loop path, the work done is non-zero. So this secondary condition is also equally important to understand the difference between conservative and non-conservative forces. So make a note of this, please. Okay, so hope this is clear. So now that we've understood this definition, any constant force F is conservative by definition, because for a conservative force, because for a constant force, we can see that the work done reduces to the simple formula of F dot S. So you can see that it is path independent. Okay. And the work done will be zero in a round trip, because the displacement will be zero in a round trip. So by definition, any constant force is conservative. So for example, of the mechanical forces we've seen, automatically we'll understand that mg, or the gravitational force, is conservative because it's a constant force now. It's a constant force. Therefore, it is a conservative force. That depends on the nature of the external force, Sanjesh. The external force can be conservative, can be non-conservative also. Like, see, the previous two examples we saw, no? One of them was a conservative force, the other was a non-conservative force. So even in thermodynamics, that thing can happen. Na? The force you're applying on a system, on an ideal gas kind of system, can be conservative, it can be non-conservative also. Okay, next, another common example of a conservative force is a spring force. Spring force is conservative. You know. Last time we had seen that work done by spring force, how it comes out to be. If the spring is stretched through a distance of x, okay, then the spring force is like this. So it is kx in magnitude, but always opposite to the direction of displacement. Whether it is like this, or it could be a case where the spring is compressed, and you're compressing it further. So at this point of time, the spring force acts outwards, okay, whereas compression, so both cases you can see whether you're compressing or extending. So this becomes minus half k, like this, because okay. So the work done by the spring, if you see now, it's a formula such that it is path independent. It only depends on final state and initial state. It's path independent. Okay. It depends on state only. Okay. So therefore, spring force is conservative in nature. You can also see that work done in a round trip will be zero. So final state is equal to initial state. So work done by spring will become zero. So that is a necessary condition for conservative force, that work done in round trip must be zero. So it is conservative. Okay. So we'll conclude the session here today. Now next time we'll see something very important, that work done by friction, kinetic friction, is path dependent, and kinetic friction will do negative work in a round trip. So kinetic friction is the physical example of non-conservative force for us. Okay, so out of all the physical examples of forces we've studied, kinetic friction is the one which will be the non-conservative force. So just make a note of this and conclude the session. If you have any doubt, please ask me. Okay, so students, that's it for today's session. So tomorrow we will continue with work by energy, and also if there are doubts pending in friction and laws of motion, please let me know which questions from the module, etc. Maybe some of the questions we will discuss in session, or maybe a doubt session, whatever. So hope you have completed most of Newton's laws and friction questions from your module, and please let me know whatever doubts you're having. Okay? That's it for today's session, people. All the best.